Now we're going to look at another example involving planes where the goal will be to determine the line which is the intersection of two given planes. In general, as you probably know, the two planes will intersect in a line. Is this always the case? Not exactly. It's possible that you have two planes which are really the exact same plane, in which case the intersection would be the entire plane. Or you can have two parallel planes that don't intersect in any points at all. In both of those cases, those planes will have the same normal vector, so it's easy to see when this will happen. If you don't have parallel planes, then the intersection will in fact be a line, and it will be easy for us to describe that line of intersection. Let's look at the planes with equations x plus y plus z equals 1 and 2x minus 3y plus 5z equals 5. You can see that the normal vector for this one we can read off. And when I say the normal vector, I mean a normal vector, because you can multiply it by a scalar and you still get the same normal, you still get a normal vector to the plane. You can read off a normal vector just by looking at the coefficients of x, y, and z. That's just the vector 1, 1, 1. I'll call that n1 for this first plane. For the second plane, we can use as a normal vector n2, which is the vector 2, negative 3, and 5. And since these normal vectors are not parallel, quite clearly, neither is a multiple of the other, these planes certainly will intersect, and their intersection will be a line. Here's our first approach. We ask the question, what is the direction vector for the line? Well, I'll try to draw a picture, though the picture will be pretty bad here. If we have one plane here, and we have another plane here which intersects, their intersection will be this line. This line will have to be orthogonal. This line will be in both planes. So being in each plane, it will be orthogonal to the normal vector for each plane. So what is a direction vector for this line? It will be a vector which is in fact orthogonal to both n1 and n2. Do we know how to produce a vector orthogonal to both n1 and n2? Yes, we can use the cross product. That will give us a vector orthogonal to both normal vectors, and that will then be a vector in the direction of the line we want. So we're going to use the vector v, which is n1 cross n2, that cross product. And if we just write down that cross product, the cross product of 1, 1, 1 and 2, negative 3, 5. Remember, there's a nice way to kind of remember how to do this. You take the vector I, the vector j, the vector k, and you look at the determinant of this matrix, where you put n1 there and n2 here. And you can read off the entries for n1 cross n2. That's just the first component, namely the multiple of I, is 1 times 5 plus minus negative 3 times 1. That would be 5 minus negative 3, which is 8. The second entry is negative 1 times 5 minus 2 times 1. That would be negative 1 times 3, or negative 3. The third component would be the determinant of this 2 by 2 matrix, which is negative 3 minus 2, which is negative 5. So now we have the direction vector for our line. Now remember, in order to describe a line, we need one point on the line, plus we need a direction vector. Well, how in the world are we going to get one point on the line? Here's another nice trick. Unless a line is parallel to one of the coordinate planes, then it will actually have to have the interesting property that you can pick any value of x and the line will contain, in fact, exactly one point with that value of x. Let me show you how that helps us. And of course, the same is true for y and z. You can pick any value of y, there'll be one point on the line with that value of y, similar for z. Let's say I have, remember, these two equations for the planes. Let me just look for a point on the plane, on both planes, find a point on both planes, meaning on the intersection, with x equals 0. Well, if x equals 0, from the first equation, we need y plus z equals 1. From the second equation, we need minus 3y plus 5z equals 5. And this is just now a system of two equations in two unknowns, and I want to find values for y and z that make this work. Well, I can do that easily. There are a variety. I could use a method of solving for one variable here and substituting, or I could add a multiple of one equation to another to simplify things. Let's try that. Let's say instead of the second equation, I'll take the second equation plus 3 times the first equation. That will make the y's disappear, because negative 3y plus 3 times y will be 0. 5z plus 3 times z will be 8z. 5, when I add 3 times 1, will just be 8. In other words, we have to have z equals 1. Then when we know z equals 1, we can easily see from either equation that y has to be 0. So our point is the point 0, 0, 1. And you can check that that point 0, 0, 1 is on both of the planes. Just plug in the coordinates and you'll see the first equation is satisfied and the second equation is satisfied. Now, how do we describe a line that contains this point and has this vector? I'll repeat it here. V equals the vector 8, negative 3, negative 5 as the direction vector. Well, we can just write down parametric equations for the line, for example, where x will just be the x coordinate here, which is 0, plus this number times t. So x is just 8t. Y is just, again, 0 minus 3t. And z will be 1 minus 5t. Here we have the parametric equations for the line. And if you want the symmetric equations, you can just solve for t in each and easily write x over 8 equals y over negative 3 equals z minus 1 over negative 5. Now let's look at another way we could find an equation for the line, or the description of the line, which is the intersection of these two planes. Instead of finding the direction vector first, we could just find 2 points on the line, and then we could just use as a direction vector the vector from one point to another. In other words, if I want to describe that line, if you find me 2 points, P0 here and P1, I could just describe the line as by using P0 and using the direction vector to be the vector P0, P1, or the other direction would work fine. So really, to describe a line, having 2 points is close to everything I need. Then I just compute the direction vector and I can get the parametric equations. So how do we find 2 points? Well, point P0 we already found. That's just the point 0, 0, 1. To find point P1, I just need to pick, for example, a value for y or a value for z or even a different value for x, and then I can solve for the other variables to find that point. I might try using y equals 0, but we already know that that would give me P0 again. So let me just try to let z be 0. Then I would have to solve these equations with z equals 0. First one becomes x plus y equals 1, and the second equation becomes 2x minus 3y equals 5, and that will give me the x and y coordinates of a point on the intersection of the two planes with z coordinate 0. Now it's easy to solve this system of two equations. I just take the second equation minus twice the first to get 0x. When I take the second minus twice the first, I get negative 5y. This minus twice that is 3. So y will be minus 3/5, and then x will have to be 8/5. In other words, my point P1 will be exactly the point 8/5, negative 3/5, and 0. So now I have 2 points, P0 and P1. I can use direction vector 5V to be the point P0, P1. And so I just subtract coordinates to get the point P1. 8/5 minus 0 is 8/5. Negative 3/5 minus 0 is negative 3/5. And 0 minus 1 is negative 1. I can use this as my direction vector. Now, what will I get if I want to find a line containing this point, say P0, and this direction vector? Well, I claim we have the same line we had before, because if I just look at the vector 5V, which is a vector in this exact same direction, so I could have used that as the direction vector for my line. This is just the vector 8, negative 3, negative 5, which you'll see was exactly the same as the direction vector we used before. And we're going to use this same point as before, so we get the same line in this manner as well.